Let me check the live stream is on. Okay, so I think everything is all set. So yeah, welcome to today's lecture on in the P&S Modern SSD course. So today we'll be discussing a very exciting and interesting topic on processing inside NAND flash memory. And I'll discuss this topic by taking one of the recent works um, and probably discussing that a bit more in a bit more detail. This work is Flash Cosmos in flash bulk bitwise operations using inherent computation capability of NAND flash memory. And this was a work that was published in Micro 2022. So please feel free to ask questions at any point, and I'll be happy to answer that. So I'll start with an executive summary. So the background is uh, s- so in this paper we focus on bulk bitwise operations, which are one of the most important primitives that are widely used primitives in data intensive applications like databases, graph processing, cryptography, etc. And the key problem that affects how these bulk bitwise operations are performed currently is that these operations are stored in the operands of these bulk bitwise operations are stored in the storage device, and the computation is performed in the host device or host system. The performance and energy efficiency of these operations are severely bottlenecked by the data movement that happens between the storage and the compute units in the traditional systems, and also in some of the new techniques like in storage processing. And if you take the in flash processing techniques, then there is the problem of data sensing or serial reading of operands, which affect the performance and energy efficiency. Now, there is another aspect that is also important, which is these prior IFP techniques provide very low reliability during the computation. And I'll discuss this in a bit more detail as we go along. So the goal of this work is to improve the performance, energy efficiency, and reliability of bulk bitwise operations. And how can we achieve this with in-flash processing? And to this end, we propose Flash Cosmos, flash computation with one-shot multi-operand sensing. This is an in-flash processing technique that is based on two key ideas. The first one is multi-word line sensing, which enables multi-operand bulk bitwise operations with a single read operation. And to improve the reliability, we also propose enhanced SLC mode programming, which increases the voltage margin between the programmed and the array states to provide high reliability during the computation. So some key results. Flash Cosmos is evaluated on 160 real 3D NAND flash chips, and we also do a system level evaluation with the state-of-the-art SSD simulator MQSIM. We choose three real-world applications for the study, and Flash Cosmos improves the performance and energy efficiency by 3.5 times and 3.3 times over the state-of-the-art IFP technique. And all this is achieved while also providing high reliability during computation. So this is a very brief snapshot of what this work is. I'll go into a bit more detail, but if you have any questions, please let me know. Okay, so let's jump into the motivation for why this kind of a technique is required uh, after all. So let's start with bulk bitwise operations. As I said, it's widely seen in many applications like databases, web search, genome analysis, cryptography, etc. So as I said, the data movement is severely affecting the performance and energy efficiency of these operations because the data is being moved from the storage device to the compute units through the memory hierarchy. for every computation, and this severely affects the performance of these operations. Now, let's look at the data movement bottleneck in a bit more detail. So currently, how these operations are performed is something we call as outside storage processing, is by moving the data to the host CPU through the memory hierarchy, as I mentioned. So here we have a kind of representation to show how this happens, and uh, we have the host processor, which could be a CPU or a GPU, and the main memory and the storage. So when the bulk bitwise operations have to be performed, the operands are read from the storage device to the memory, main memory, and from the main memory to the host CPU or the GPU. And if we look at and then the computation is performed in the host CPU or GPU, and then the data is written back to the result is then goes through the memory hierarchy and is stored in the storage device. If you look at the bandwidth of the storage, external I/O bandwidth of the storage device and the main memory bandwidth, we see that the main memory bandwidth is significantly higher than the storage I/O bandwidth, which is typically around 8 to 10 Gbps. And this is the main bottleneck that is affecting the large data transfer that happens through the memory hierarchy. So this limited bandwidth is what is causing the performance and energy efficiency to be, or what affects the performance and energy efficiency. Now, there is this paradigm of performing computation where the data resides, or near data processing. And there have been several works that have been proposed to perform NDP for bulk bitwise operations. And we see that at the cache hierarchy, we have compute cache, ambit near DRAM, and then Pinatubo for NVM. And for in storage, we have Biscuit from 2016, and then also for in flash, we have Parabit. So these are some of the works that look at bulk bitwise operations very closely, and the main area of the main focus for us in this work is to look at in storage and in flash processing, because if we have large data sets that do not fit in the main memory, then these data sets have to be stored in the storage device, and this is where in storage and in flash NDP techniques are useful. So we start by looking at in storage processing. So if we look at in storage processing, the ISP, as we call, performs computation using an in storage compute unit, which could be embedded cores or FPGA. And ISP reduces the external data movement by transferring only the computational results to the host. And we see how this happens. And we see the same representation, but in this case, we see the storage device, a more closer look at the storage device, where it has an in-storage compute unit, and then many NAND flash chips where the data is stored connected through flash channels. Now, if the computation has to be performed in storage, then the data is being read from the flash chips, large amounts of data, and then the computation happens in the in-storage compute unit. And then only the result gets transferred outside the storage device through the memory hierarchy. Now, if we look at while the data that is being transferred outside the memory, the storage device is reduced, we see that still a large amount of data is being transferred from the flash chips to the in-storage compute unit. And if we look at the bandwidth of these flash channels, we see that it's around 9.6 Gbps, which is not significantly higher than the external I/O bandwidth. And this remains the main bottleneck for in-storage processing, the transfer of data across the flash channels. Now, so the internal bandwidth is the main bottleneck in ISP. Now, if we look at in-flash processing, and in-flash processing is a paradigm where we move the computation more closer to where the data resides, and we are performing the computation actually where the data is stored. So here, this is how the state-of-the-art IFP technique does, which is perform computation within the flash chips by reading the operands serially. And IFP significantly reduces the data movement that is done outside the flash chips, but there is also this challenge of serial reading of operands, which I will show in a while. So again, we show the same representation of host CPU or GPU, main memory, and the storage device. And here we immediately see that the computation is performed in the flash chips, and only the result is being transferred through the flash channels to the in-storage compute unit and externally into through the memory hierarchy. Now, so as I mentioned, in the state-of-the-art in-flash processing techniques, the main challenge is that to perform these computations, we need to perform serial sensing of operands, or we need to read each operand and perform the computation. So that's the main challenge in this kind of an approach, because the latency of a read operation is very expensive. Now, we look at the data sensing bottleneck in IFP in a bit more detail and see that so the state-of-the-art IFP technique performs bulk bitwise operations by controlling the latching circuit of the page buffer. So if we look more deeper into the organization of a NAND flash chip, we see that each NAND flash chip has, this is a very simplistic representation of a flash chip, but essentially we have several flash pages where the operands are stored, and a page buffer, which is a temporary buffer that is being used for moving data during program or read operations. So let's assume there are multiple operands that are used for bulk bitwise operations stored in these flash pages. The way the state-of-the-art technique, IFP technique does bulk bitwise operations is by reading one operand at a time. So you read operand A, then you go on and read operand B, and by controlling the latching circuit, you get the result of a bitwise AND operation in the page buffer. So that's between two operands, and then if you read another operand, then you would get the bitwise AND of three operands, and so on. So if there are let's say 48 operands or 100 operands, then you need to do 100 reads to perform this bitwise AND operation. So the serial data sensing is the main bottleneck to which affects the performance of IFP techniques. Now, the reliability is another issue that affects the current IFP techniques, and I'll tell you why. Because NAND flash memory as a substrate suffers from very high raw bit error rate. This is because of many disturbances. The ECC and data randomization techniques are typically used to improve the reliability of flash memory. But these prior IFP techniques cannot leverage the ECC and data randomization techniques, because the computation is performed within the flash chips, and these mitigation techniques are residing in the SSD controller, which is far away from where the computation happens. So there will be a lot of data movement if we need to make the data more reliable by using the ECC engine. So because the computation is happening only in the flash chip, these IFP techniques do not use these kind of mitigation techniques that are typically used in commodity SSDs. So in prior IFP approaches, they suffer from erroneous computation results, and this is because of the high raw bit error rate of NAND flash memory if they don't use the ECC and randomization techniques. So we look at an example here where there are errors in the operands because of many disturbances, and when the data is being read in a serial manner, the errors get propagated and stored in the result, and it can also get compounded because of errors in the other operands as well. So this can result in um, a very noisy or erroneous computation result. So the requirement of applications or these IFP techniques require the applications to be highly error tolerant, and only then these kind of techniques can be utilized. So our goal in this work was to address the bottleneck of state-of-the-art IFP techniques, which is uh, to basically fix the serial sensing of operands, and then also make IFP more reliable, which is to provide accurate computation results. So I'll give a brief idea of how Flash Cosmos operates, and it's very simple, as I mentioned. It enables computation on multiple operands using a single sensing operation, and it provides high reliability during in-flash computation. So if we see the same representation of a flash chip, and the operands are stored in many flash pages. So with Flash Cosmos, the result of the bitwise operation happens in a single read operation, and you would get the result of the bitwise and of multiple operands at the same time. So as we see later, we can do this up to the number of pages that are available in the flash block. And for bitwise OR, we can perform these computations across blocks as well. And we also show the technique to improve the reliability of such operations. So that is uh, the motivation for this work. And if you have any questions, please feel free to ask, and I'll be happy to answer. Let me check if there are any questions on YouTube. Okay. Okay, so let's jump to the background. So the background is background section mostly gives us some idea of what a flash or gives us more details into the flash organization, flash memory organization, and also some of the insights that we use to design the MWS operation. So we'll start with a flash cell, and you may have seen this before. A flash cell stores data by adjusting the amount of charge in the cell. And if a flash cell is in the array state, then it stores the value 1. That is, it has a low charge level. And if it's in the program state where the charge level is high, it stores the value 0. And if we activate the flash cell, then if it is in the array state, then it operates as a resistor. And if it's in the program state, it operates as an open switch. Now, if we combine a bunch of flash cells and connect them in a serial manner, then it's called an NAND string. And each NAND string is connected to a bit line. And during a read operation, if we want to read a particular NAND flash cell in the NAND string, then we consider the other cells in the NAND string as non-target cells. And we essentially do this by sending a high read voltage to these cells. And because of that, they operate as resistors irrespective of what data is stored in these cells. And if the target cell stores the value is in the array state, then it operates as a resistor. Or if it's in the programmed state, then it operates as an open switch. So during a read operation, when the when the bit line current passes through the NAND string, if the target cell operates as a resistor, then the bit line current passes through the NAND string and the sense amplifier decodes it as a value 1. If the target cell operates as an open switch, then the bit line current passes through the NAND string and it gets blocked because of the open switch. And then the sense amplifier reads the value as 0. So this is a key principle that we use in our multi-word line sensing. One of the key principles that we use in the multi-word line sensing mechanism, the read operation. Then, if we kind of lay out these a number of NAND strings in a horizontal manner, which are connected to different bit lines, we get the flash block. And if we connect the flash cells at the same level across different bit lines, then it forms a word line. And a single word line controls a large number of flash cells, and it provides high bit level parallelism. Now we go to a more higher level and see that there can be thousands of flash blocks in a flash device or in a storage device, and these flash blocks share the same bit line. So you can see that there can be a number of bit lines that are common across these flash blocks. And here we kind of look at two principles which are which form the key ideas of Flash Cosmos. So if you look at the cells connected in the same block, connected to an AND string, then we see some similarity with digital AND logic, which is where two transistors are connected in series, in series, and that gives the two input and output. So this is one principle that we use for designing the MWS operation. And we also look at the cells connected in different blocks. And these are connected in parallel because the NAND strings are unique to each block. And here we see that this is very much similar to the two input OR logic. And we also use this for performing the OR operation. So yeah, so this is basically a bit of background on the on flash memory organization, and also the key insights that we derive for performing for some of the key techniques of Flash Cosmos. Any questions so far?
Yes, I have a question.
Yes.
Does the voltage that we need to apply to the path, I think it's called V-path or something, right?
Yes.
Does it change the amount of charge that's in the trap, or does it have no influence on that?
Yeah, that's a very good question. So yeah, so this is basically for the non-target cells, we provide a V-pass voltage, which is very high compared to the read voltage. It has some influence on the neighboring cells and also on the cells on which the V-pass voltage is provided. And we call this the read disturbance phenomena in flash memory. So as we read these, as we provide the VPass many times across a large number of reads, then it can actually create a sort of pseudo programming effect on these cells, and that can result in some disturbance and loss of data, or disturbance in the data. So that has an impact, but there are also mitigation techniques that are present in the flash memory or devices to mitigate such techniques.
Okay, thank you.
Yeah. Any other questions? So, so let's jump to the key ideas of Flash Cosmos. So the first key idea of Flash Cosmos is to enable in-flash bulk bitwise operations on multiple operands using a single sensing operation. And we call this multi-word line sensing. And this multi-word line sensing sensing technique has two variants. The first one is called intra-block MWS, where we simultaneously activate multiple word lines in the same block. And this variant or this technique provides as the bitwise AND operation. And as we saw earlier, we see a block, NAND flash block, where there are multiple word lines, and there are several bit lines to which the NAND strings are connected. So if here we show an example where two word lines are being simultaneously activated, and the rest of the word lines are operate as non-target cells or resistors. So when we, depending on the state of the cell, again, we see that if it's in the programmed state, then it operates as an open switch. If it's in the array state, then it operates as a resistor. So when we simultaneously activate all these bit lines or all these word lines, the bit line current tries to pass through the NAND string, and depending on whether there is an open switch or a resistor, the bit line current passes through the NAND string. So the result, the output of a bitwise AND or this intra block MWS can only be a 1 if when all the target cells store 1, which means that all the target cells have to be in the array state. And this is the equivalent of a bitwise AND of the target cells. And the reason, as I mentioned, is that only if they operate as resistors, then the bit line current can pass through the NAND string. Now, if we see here, we show an example where 4 word lines are being simultaneously activated. And in none of the bit lines, the value is read as 1, or everywhere it's read as 0, because all of them have an open switch as one of the cells in the NAND string. So a bit line reads as 0 even if one target cell stores 0. So intra-block MWS enables the bitwise AND operation of multiple pages in the same block, and it does it with a single sensing operation. So now we look at another variant of MWS operation, which is bitwise inter-block MWS, which helps us perform bitwise OR. And we achieve this by simultaneously activating multiple word lines in different blocks. So here we show 2 different blocks. So the block representation is shown in yellow here. And as we saw earlier, the bit lines are common across different blocks. And we activate 2 word lines across these blocks. And because, and then the bit line current passes through each of these NAND strings. And here, if a bit line is read as 0, only when all the target cells store 0. So which means that if both the cells operate as open switch, only then we read the value as 0, which is similar to what bitwise OR operation, the result of a bitwise OR operation. And if we see an example with 3 word lines across different blocks, then we see that even if there is a single NAND string connected to the bit line, which has all the cells as operating as resistors, then we see the result as 1. So this is because they are all connected in parallel, and then the bit line current flows through all these NAND strings. So this is the equivalent of a bitwise OR operation. and interblock MWS enables bitwise OR of multiple pages in different blocks with a single sensing operation. So if you go through the paper, you would understand that we have a limitation in terms of how many interblock MWS operations can be performed. We currently restrict it to 4 interblock MWS operations, which means that the main reason is because of the power budget of the SSD, which is activating these word lines across different blocks require more power consumption than an intra-block MWS operation. So that's the key reason for reducing the number of interblock MWS operations supported in Flash Cosmos. So now we have looked at intra-block and interblock operations, MWS operations, and we also support other bitwise operations in Flash Cosmos. So we support bitwise not by exploiting the inverse read operation, which is already supported in flash memory by mainly for performing copyback operations. Then we also can perform bitwise NAND and NOR by using the inverse read operation and essentially performing using De Morgan's law to with bitwise AND and OR. And there is also bitwise XOR and XNOR supported because XOR is already supported between the two latches, the sensing and the cache latch in flash memory. So these are this is how we support different bitwise operations in Flash Cosmos. So I'll move on to how we improve the reliability of in-flash bulk bitwise operations. And we propose a technique called enhanced SLC mode programming, which is a very simple technique to improve the reliability of these computations. So let's look at ESP. ESP is very similar to SLC mode programming. And because SLC mode programming already provides a large voltage margin between the array state and the program states. There is a trade-off in terms of the density of the flash cell versus the reliability here. So if you store less number of bits, the reliability goes up because there is a wider margin between the two states. And this is a representation of the voltage distribution of the cells in a word line. And some of them are in the array state, some of them are in the program state. Now, so there's already a large voltage margin. But this voltage margin doesn't actually help in case of even if it's SLC mode programming, but if we don't use ECC and data randomization, it's still prone to errors and disturbances. So the main idea is that some of these program cells can lose their charge and move back to the array state, and array state cells can move to closer to the program state. So these things can happen due to various disturbances. Now, ESP further increases the voltage margin between the erased and the program states, and a wider voltage margin between the two states improves the reliability by making the cells less vulnerable to errors. So here we see that with ESP, the voltage margin is further increased, and this is done using by performing additional steps in the incremental step pulse programming technique, which is the typical technique used for programming in flash memory. And we increase the voltage margin using this technique. So here you can see that the voltage margin is also much wider, and also the distribution of flash cell has become much more leaner compared to the previous technique. So ESP improves the reliability of in-flash computation without the use of ECC or data randomization techniques. And ESP can improve the reliability of prior approaches as well if they increase the voltage margin of the programmed and the array states. So now we have discussed these two techniques, but how do we enable these techniques to the application or to the SSD controller? How do we expose this to the SSD controller? So to do this, we use new flash commands, and I'll briefly discuss this. So we support 3 new flash commands for Flash Cosmos. The first one is called MWS command, which is used for intra-block and inter-block MWS. And also it provides support for inverse read operation and accumulation of results of all the reads. Excuse me. Then there is also this ISCM command slot, which is part of the MWS command sequence. And this allows the flash controller to control 4 features. One is the inverse read operation that I just mentioned. Then it also supports initialization of the sensing latch and the cache latch, and also moving the data from the S latch to the C latch. So I'll go into a bit more. I'll explain this with an example. Then we also support a page bitmap, which is used to specify the word lines to be activated for MWS operations. And also this page bitmap can be expanded to 4 address slots, or this address slot is you can provide 4 addresses for different word lines across 4 different blocks, and that is required for the inter-block MWS command. There's also the ESP command for improving the reliability, and that simply works like a regular program command, but performs more ISPP steps as part of the programming sequence. And then the XOR command performs the bitwise XOR between the sensing and the cache latches. And then it stores the result in the cache latch. So these are the 3 new commands that we support for Flash Cosmos. Now, so let's look at an operational example of how to perform these bunch of bitwise operations that I show here. You have 3 bitwise AND operations along with the bitwise OR in the first part, and then there is a couple of bitwise AND operations and bitwise OR operations here. So if you look at the second half of this logic equation, then we see that the bit vectors C and D are basically, although they are in their true form, we actually invert them and then store them in the different blocks, block 3 and block 4. And that is to perform more bitwise AND operations rather than OR operations. As I mentioned earlier, there is a constraint on the number of OR operations that we can perform. So these inverse values of these operands are stored in block 3 and block 4, and we issue an MWS command with the following flags. Here we see that the first bit is for the inverse read operation, and then we also initialize the sensing and the cache latch because this is the first operation that is being performed, and also we move the data between the 2 latches. So by doing this, by sending the different blocks that we need to perform, for which we need to perform the bitwise OR, and this also gives us the bitmap for the bitwise AND operation. We essentially perform the second half of the logic equation. Then if we jump to the first half, where we have 3 bitwise AND operations and an OR operation. Here, what the difference is that if you notice the ISCM flag, we don't initialize, since they're all being stored in their actual form. We don't invert the data, and we also don't initialize the sensing and the cache latch, because the output of the previous or the second part of the logic equation is already there in these sensing and cache latches. So this means that we cannot initialize it again, and then we accumulate the data in both the latches. So this MWS command is for performing these this first half of the logic equation. And so by disabling the initialization of latches, we accumulate in both sensing and the cache latches. So that's pretty much a snapshot or a brief explanation of what are the key ideas of Flash Cosmos and how we provide support for Flash Cosmos at a system level, or at the level of the SSD controller, and then an operational example to describe how the MWS commands are sent. Any questions at this point?
Yes, I have a question. Could you just go back one slide, please?
Yes.
Yes, thank you. So when we disable the initialization of latches, which operation is then performed if we do two MWS after each other?
So the result of this part, which is the first part of C1 or with C3 and D2 or with D4, is already stored in the sensing and the cache latch. So
Yes.
we disable the initialization, and this MWS operation will perform, let's say, the bitwise AND of these four operands, and then perform the OR with A1.
Yeah. And then it will save it both into the same latch.
It will save it both to the same latches. So you would override the sensing and the cache latches, and the updated result would be there in those.
And we save both to the same latch, then is this what kind of operation is that? Is that also an AND operation, or what is that? Then?
So I did not get your question. So you are saying,
so like we have like 1 and 2, they're the two different halves of the equation that we wanted before, right?
Yeah.
And so I don't get how we combine those two in the end.
Yeah, so how we combine is basically I mean, as I said, it is based on the initialization of these latches. So when we send both these MWS operations, the results get accumulated in the same sensing and the cache latch. So it basically, you can treat it as, let's say, like how in Parabit we can perform an additional sensing operation, and then the result would get accumulated on top of the existing data, right? So you can think of something like that. So you would already have some data in the sensing latch, and when you perform these MWS operations, the result, the data in the sensing latch also becomes an operand for the next part of the next stage of the MWS operation.
Okay. I think now I get it. So this accumulation itself is also kind of a logic operation then.
Yes.
Okay. Thank you.
Any other questions? Okay, let's move on to the evaluation of this work. And so in the evaluation methodology, we evaluate Flash Cosmos using 160 real state-of-the-art 3D NAND flash chips. And we'll start with that. And this is basically a real device characterization where we validate the feasibility, performance, and reliability of Flash Cosmos. And we use 160 48 layer 3D TLC NAND flash chips. By 48 layer, we mean each block has 48 word lines. And we have tested around more than 3 million word lines and under worst case operating conditions, which is 1 year retention time at 10,000 P cycles and using worst case data patterns like checkered patterns and so on. So the results of the real device characterization, I'll just give a brief overview of this. And I would refer you to the paper for more details on how for the results of the real device characterization. So both intra and inter-block MWS operations require no changes to the cell array of commodity NAND flash chips. Both MWS operations can activate up to 48 word lines in case of intra-block and up to 4 word lines in inter-block at the same time, and it can also this comes with an small increase in sensing latency of less than 10%. And ESP significantly improves the reliability of in-flash computation, and we observe 0-bit errors in the tested flash sets. Now we move to a system level evaluation where we use three real world applications to perform bulk bitwise operations. So our evaluation with real world applications was done on MQSIM, a state-of-the-art simulator which models the performance of Flash Cosmos and the baselines. We use 3 applications, as I mentioned: bitmap indices, where we typically perform bitwise AND of up to 1,000 operands, image segmentation, which performs bitwise AND of 3 operands, and K-click star listing, which performs bitwise OR of up to 32 operands. And we implement some of the baselines, such as outside storage processing, a multi-core, which models a multi-core CPU, in-storage processing, which models an in-storage hardware accelerator, and Parabit, which is the state-of-the-art in-flash processing technique. So in terms of results, we show the performance and energy efficiency. Here we show in the first part of the figure on the left, we show the speed up over OSP on the y-axis and different workloads on the x-axis. So and on the right, we show the energy efficiency over OSP, or the outside storage processing technique. And we show for different workloads the energy efficiency here. So Flash Cosmos provides significant performance and energy benefits over all the baselines. So you can see that compared to ISP, we see around 25 times improvement in performance and 13.5 times improvement in energy efficiency. And compared to the state of the art, we also observe significant benefits. And these benefits improve only with the increase in number of operands. So the more operands we simultaneously read as part of our MWS operation, the energy benefits would be higher, or performance benefits would be higher. So that is a very brief description of the results. So there are a lot more details in the paper in terms of explaining these workloads and the real device characterization and the results from those experiments. So I would refer you to the paper, and this is the link to the paper. So in summary, Flash Cosmos is the first work to enable multi-operand bulk bitwise operations with a single sensing operation, and provides high reliability. It improves performance by up to 32 times on average over prior techniques. Energy efficiency improvement by up to 95 times over OSP, Parabit, and ISP. And all of these comes at low cost and requires no changes to the flash chips itself. We need some changes to decode the MWS operations and the new commands in the peripheral logic, but that is also that those changes are also very limited and does not add add any significant cost to the area or the storage. So that's what I had to discuss for processing inside flash memory. And if you have any questions, please feel free to ask. Okay. Let me check YouTube. I don't think there are any questions there also. So if there are no questions, then we can close this session and yeah. Okay. Thanks everyone for attending this meeting, and I hope this was an interesting session on processing inside NAND flash memory, and we will meet next week for a different topic. Thank you so much.
Thank you very much. Have a good
Thank
evening.
you, Rakesh.
Evening.
Bye bye.